good day everyone, and we meet yet again. And it's been a while since I last posted, but yes, we are back again. And today I want to cover electrochemistry, and this is basically following up on the lesson on the galvanic cell that I posted. But this time I'm going to be looking at the electrolytic cell. All right, so if you haven't subscribed, please just do the right thing, okay? And by the way, you are also welcome to just put some comments, and anything that you may request for us to post in future, just put it up there and we'll see how we can attend to it. All right, so let's get started with our lesson. So first of all, starting with electrochemistry. We tackled the galvanic cell initially, and we said the galvanic cell, or in the galvanic cell rather, this is where we are converting electrical or rather chemical energy into electrical energy. But this time around, we're looking at the electrolytic cell. Now, the typical structure of an electrolytic cell. Okay, so we've got a battery that's connected there, okay, and we've got electrodes. It's connected to the electrodes over there, and let's say this obviously would be your positive side of your battery, this would be your negative side, and there are your electrodes over there. Right, now what tends to happen, so they put this in an electrolyte, which is a solution that can conduct electricity. Right, so essentially this is what an electrolytic cell does. So first of all, we know that an electrolytic cell converts electrical energy. So here we are converting electrical energy into chemical energy. So in essence, we're trying to convert reactions that would otherwise not take place. You're forcing them. So these are non-spontaneous reactions, right? So you're forcing them to take place by introducing an electrical current, and you'll see that in just a little while. Okay, right. So what I want us to do first of all is to take the process of electrolysis, and we're going to build up and look at purification as well as electroplating. So we're going to look at all of those three processes, okay, back to back, and let's get right into it. So the first example that I'm going to make is an example whereby we've got copper chloride in the solution. So what they typically do is that they will use, okay, rods that are actually made out of graphite, okay, because it's a semiconductor. So they use graphite rods, all right, and in this case, on the positive side of the cell. Now, please, I want you to listen to this carefully. So obviously, when I connect this on the positive side of the cell, it makes this portion here to be positively charged. Makes sense, right? So the positive side of the cell makes this electrode to be positive, and the negative side of the cell makes this guy to be negative, this electrode to be negative, okay? Now, typically what we have is that copper chloride, obviously being a salt, it's able to ionize, or you can say dissociate, all right? And when it ionizes, it becomes copper 2+, and you also have Cl- ions. Obviously, I've got two of them there, so I would have 2 Cl- over there, all right? Now, meaning that when I look at this electrolyte over here, it contains, all right, in this case, cat ions, and in this case, our cat ions are copper 2+ ions, and it also contains N ions, which are Cl- ions, okay? Now, let's say for argument's sake, this is electrode P and this is electrode Q. Want to find out what type of reaction is going to take place at electrode P, right? Now, please, I want you to remember, In this case, what do I know about electrode P? Electrode P has now become positively charged, and as a result, it's going to attract the negatively charged ions, right? So it's going to attract my N ions, all right? So makes sense, right? Unlike charges attract, so in this case, the positively charged portion will attract the negatively charged ions. So what reaction takes place? So I'm going to have, all right, on electrode P, I'm going to have the Cl minus ions, okay? Now notice in this case, I had 2 Cl minus. Now you may wonder where I'm getting this, but I'll show you in just a little while. Please do not take the double arrows, okay? Just like I want for the galvanic cell, here you will take only one arrow to show that this is the actual reaction that is taking place. So 2 Cl minus will now convert into Cl2, all right, by giving away 2 electrons. Now let me show you quickly how are you going to actually find that reaction. So if you go to your standard potential table, which you are given, all right, let's look for the Cl minus half reaction, or the chlorine half reaction. Okay, there it is over there. Okay, so this is the fourth one from the bottom, or the fifth one. 1, 2, 3, 4, 5. Okay, there it is over there. Okay, now you see there you've got Cl2, which is a gas. Now notice we didn't have a gas initially, we had the Cl minus ion. So what are we going to do? We're going to take this reaction and it's actually the other way around, turn it the other way around. Okay, so that's the reaction that's going to take place. Cl minus will convert to Cl2 by giving away 2 electrons. So I hope that you could see that. That's where we got that reaction there. So that's the reaction that takes place at electrode P. And then, so which means at electrode P, I am likely to see some bubbles forming, right? And what are those bubbles that will be forming? Those bubbles would actually be formed from the chlorine gas. Okay, so I'm just going to show them over there. Okay, there's a question that I remember that they asked, where they say state the changes that take place that would be observed in the cell. So the first change that you would observe is that there'd be bubbles that are forming, and in that case, those bubbles are because of the chlorine gas that is formed over there. And then secondly, let's now talk about electrode Q. All right, so what reaction is taking place at electrode Q? All right, so at electrode Q, remember now, we said electrode Q is negatively charged, so it would tend to attract those cation ions over there, the positively charged ions. So in this case, remember this guy is full of electrons, so in this case I'm going to have copper 2 plus. Okay, now your copper 2 plus ions are going to now receive electrons, are going to gain electrons and become copper. Okay, so they're going to change to copper again. Let me show you from the standard potential table. Okay, right, I'm going to take that one there. It's copper 2 plus. This is what I had initially. You receive 2 electrons and it forms into copper, right? So in this case, I want you to note this is the reaction that takes place at electrode Q. All right, which is something very unlikely, but they might ask this. Okay, so please remember what would be the net cell reaction that takes place here. So to get the net cell reaction, you remember you need to make sure that the number of electrons that are given and the ones received are basically balanced, so that you can get a balanced reaction. So at the end, if I take those two reactions, I've got copper 2 plus, okay, plus 2 Cl minus. That is actually copper chloride. Okay, and they basically become, so take everything that's on the right hand side, this becomes Cl2 plus copper. Now please remember, ladies and gents, this reaction could not take place unless I introduce an external source of energy, and in this case it's electrical energy. So Typically, this is what happens in an electrolytic cell. You are converting that electrical energy into chemical energy, or in this case, you're driving a chemical reaction by using external electrical energy. Right? Now, just quickly, before I move on to the other cell, what are the other changes? Now, we said, first of all, we are going to experience, we're going to see bubbles that are forming there, right? But what's another reaction, or what else would actually take place? Of course, as you form copper, remember copper is this bronzish brown metal that forms. So obviously over here, you'd see that buildup of a metal that is forming on electrode Q, that brown metal that's forming. But another one which would not be which is not quite that straightforward. So you would have copper 2 plus ions. Now copper 2 plus ions, your copper ions usually, especially the 2 plus ions rather, are blue in color. So this solution over here would typically be a deep blue color. But the more the reaction takes place, remember, I'm using up those copper 2 plus ions and I'm converting them into copper. So as a result, what would typically happen is that you would end up having that blue color kind of beginning to fade. So three things that would happen. We said a gas would be formed at electrode Q. Okay, so that gas is chlorine. So gas formed at electrode P. All right. Secondly, we said another thing that would happen is that a metal would form at electrode Q. Okay, and of course it would be, in this particular case, a sort of brown bronzish metal that is forming. And then thirdly, what would happen obviously is that the solution would move from a deep blue color to more of a clear colorless sort of solution. Okay, so it would move from blue, look, it wouldn't get to a point where it's completely colorless, but obviously the amount of blue color there would tend to be faded. Okay, right, so this is the first type of a reaction. This is called electrolysis. Now please, I want you to note there, remember what is electrolysis. Okay, you need to be able to state that. We said it. We say it's the process of using electrical energy in order to break down compounds and form new ones. Okay, so it's the process of breaking down compounds, forming new ones by using electrical energy. Okay, right, now let's go to the second type of an the electrolytic cell. Right, so the second type of an electrolytic cell, or the second process in an electrolytic cell, is what we call purification. Okay, so what happens under purification? This is where we are taking a metal, okay, or a metal ore, okay, or an impure form of the metal. Now, please, I want you to note, ladies and gents. Okay, so suppose I just take there, let's say I've just mined silver, and obviously this silver would have impurities in there, right? Okay, and what I'm trying to do is just to purify it. So now, please, I want you to note what would happen typically. Okay, so what they would do is they would put, now please, I want you to note, this is obviously the ore part, the impure part of silver. This would be pure silver. All right, so you basically want to break this guy down, okay, and form pure silver. You want all the silver particles, or the silver the silver particles, let me call them that, right, to go there and actually form more of the pure silver. All right, so note at electrode, let me call it electrode X, let me call that electrode Y. Okay, now I'm leaving this deliberately as it is. Of course, you would connect this to a battery. Now I wanna show you something very quickly. Right now, ladies and gents, under purification, the one that I want to break down, okay, right, because I want to show you something quickly. The one that I want to break down, I would actually connect to the positive side of my cell, okay, and the one that I want to form, and I'm going to show you why that is the case, okay, right. So on the positive side, that's the one that I want to break down, okay. On the negative side, that's the one that I want to kind of form, purify in a sense, okay. So I want the impure particles to kind of fall away. I want the silver particles to move from here and go there, right? Now, typically, ladies and gents, how would I make sure that only silver goes there? Now, you'll note in your standard potential table, okay, if you take silver there, which is He over there, it has a standard potential of 0.8. So you have to make sure that you connect a battery that has a potential of 0.8 so that only the silver particles obviously would respond to the amount of energy that you've given there. Okay, so now what would happen at electrode X? Now please, I want you to note you've got silver, pure silver over there. All right, now what you would have is that at electrode X, the positive electrode, you'll have silver now begin to break down and form silver ions. Okay, so all the silver that's there, it would go into the solution and form Ag plus ions. Okay, right, but at the same time, by the way, by actually giving away an electron, and by the way, once again, you can use your standard potential table to see that half reaction take place there. Okay, so you've got Ag plus an electron giving you Ag, but we know that we are actually now reversing that process. So it's actually the other way around at electrode X. Let me call that electrode X, right? So that you can see. Now, the beautiful thing about purification process is that the reaction that takes place, okay, so if you think about what we said about the galvanic cell, right? We said, what type of a reaction is this? This, in this case, it's the loss of electrons. And we know that the loss of electrons, okay, how do I know it's a loss of electrons? Or the giving away of electrons? Because you started with silver, okay, that has electrons in it. And now it became silver plus iron. All right, how did it do that? By giving away this electron, okay? So it's the loss of electrons. So in the galvanic cell, remember that oxidation took place at the anode and your anode was negative. But in the electrolytic cell, I want you to notice that your anode now, okay, your anode is the positive part of the cell, okay? Why? Because remember we said at the anode, this is where oxidation takes place. So we know that oxidation takes place at the anode. So remember that in the galvanic cell, the anode was negative, okay, right? But in the electrolytic cell, now the anode is positive, and this is where oxidation is taking place. That's at electrode X. So what's happening at electrode Y? Remember, electrode Y is connected to the negative side of the cell. So it means this guy simply becomes negatively charged, right? But now what begins to happen? All those positive ions, okay, now get attracted to that side of the cell. So in this case, what happens is that Ag plus ions now begin to gain electrons, okay? So goes there, gains an electron, and what happens? It means that now it becomes pure silver. So in a sense, what you end up having here is that this guy becomes bigger and bigger, but as it becomes bigger, it's actually made out of just the silver ion, okay, the silver particle, okay, right? So more silver is actually formed at that point there. All right, okay, so I hope that makes sense. Now, just one other thing that I want to mention, okay? Obviously, now we know that the cathode, it means that our cathode would be the negative side or the negative part of your cell, right? So in this case, what determines whether it's the cathode or the anode? It's the actual cell itself. Now you put a battery there. The battery, this is the positive side of the battery, the negative side, and in this case, it drives that process. Now, what I also want to just quickly show you is that what would you normally do when you want to purify silver? You would make sure that the electrolyte that you use, remember that an electrolyte is a solution that can conduct electricity, right? So in this case, the electrolyte that you would use would be a silver electrolyte in a sense. So remember that electrolyte must be soluble. So typically, which electrolyte would you use? Okay, I like nitrates, okay? So I would use silver nitrate because remember, all nitrates are soluble. Okay. By the way, if you were purifying, let's say, another metal, let's say copper, for instance, it would actually make sense to use copper nitrate because it's also soluble. Okay. You wouldn't want to use silver chloride because it makes precipitates, but that's another story for another day. Okay. So in this case, what we simply are saying is that for purification, remember the half cell that you form. Look at this. It actually becomes easier because what happens at X, all right, at the one electrode, it's actually just the opposite on the other electrode. Okay, so I hope that makes sense in terms of that cell. Or just another question that they normally ask. Okay, they would say to you, can you comment about the concentration of this solution of the electrolyte here? So the concentration of the electrolyte would actually stay the same. And why is that? Because the rate, remember, the rate of oxidation here is equal to this to the rate of reduction. So reduction takes place at your cathode there, but at the same time that you are busy forming those silver ions there, at the same rate, you are also taking them away and forming silver from them. Okay, so the rate of oxidation is actually equal to the rate of reduction. I hope that makes sense. Now let's take the last reaction. Okay, and we would kind of wrap this up. It's quite a simple and easy section, this, and it's not worth a lot of marks, so we won't dwell too much on it. Okay, so let's take the other one. So the last process that we want to talk about is called electroplating. All right, so this is typically just taking a cheaper metal, okay, a metal that would get easily oxidized, and coating it, all right, plating it with a more expensive, more precious metal. If you think about the watches that we normally use or the rings that we normally use, okay, they are actually plated. Most of them are actually plated with a precious metal, for instance, gold or platinum or whatever the case is. So let's talk about a typical electroplating process. So suppose we've got, let's say we've got a ring, okay, that you want to plate. Remember, my drawing skills need prayers. Okay, so what I would have there is, let's say I connect it. So once again, remember I said whatever I want to form, I connect to the negative side. Whatever I want to break down, I connect to the positive side. So the pure metal, all right, so let's use platinum as an example. I want to plate a ring with platinum. Okay, so I'm going to connect the pure platinum on the positive side. I'm going to connect my ring because I want the platinum to come this side. Okay, all right, so I'm going to connect the ring, okay, to the negative side of my cell. Okay, by the way, maybe let me just state this categorically. It's just by pure coincidence that I made my positives to be on the left hand side. I'm not in any way trying to say that they'll always put the positive side on the left hand side. Okay, right, so you just need to know the process so that you can be able to differentiate between your positive and your negative. Remember that oxidation would always take place at your anode, and your anode is the positive one. Okay, so it doesn't have to be at the left hand side necessarily. Right, now ladies and gents, what we want to do is to coat this ring with a precious metal, which is platinum. So let's say we take a cheaper form of metal. Let's say we take nickel. All right, and we are going to now take a nickel ring, and we want to cover it up with platinum. Okay, so that it's not a platinum ring, but it's a platinum plated ring. Okay, so now what would happen? So at the positive, remember, we've connected this guy to the positive, so what happens? This guy would be positively charged. Okay, and obviously we've connected this ring to the negative side, and it would be negatively charged. Now going to your typical to your standard potential table, once again, there's my platinum over there. Okay, so in this case here it is Pt2 plus 2 electrons forms Pt. Okay, so in this case I know that my platinum, okay, let's give the electrodes another name. Let's say that's M and N. All right, so what happens at electrode M? Okay, so at electrode M, I know that I would be taking that platinum and I'm breaking it down. So platinum breaks down, undergoes oxidation. Okay, so it becomes Pt2 plus by giving away, okay, 2 electrons. All right, so it undergoes oxidation in this case, and it becomes a platinum ion. And then at electrode N, once again, all right, just like the process of the previous process where we were purifying rather. Okay, so it's going to be exactly the same half reaction, only this time in reverse, right? So therefore, on this one, so you have those Pt2 plus ions, okay? And by the way, it could be any other metal. Okay, I'm just using platinum as an example. So I'm making those Pt2 plus ions. Okay, and now they are going to receive an electron over there. This guy is charged up and full of electrons, and in this case, therefore, it would become platinum. So in this case, it means that this ring now would be full of platinum particles over there, or platinum coating. And then obviously the last part would be just the polishing of it. Okay, and you'd have that bling bling, money ain't a thing, you'd have that ring, that beautiful shining ring. Okay, right, they do this to watches or anything of the sort. Okay, so therefore it would be plated. Okay, so once again, typical process, you'd have more or less the same thing when it comes to electroplating. Okay, and by the way, just look out for the next video where I'm going to be looking at past exam questions where we apply this. Okay, but essentially, ladies and gents, these are the 3 processes that have to do with the electrolytic cell. We talked about purification, we talked about electroplating, we talked about the process of electrolysis. And I'm gonna look at past exam questions in my next video. And thank you so much for watching. Please don't forget to give a thumbs up to this video if you liked it, and please don't forget to also subscribe if you haven't, and I'll see you guys next time. Sharp sharp.